We are the statisticians. Oh, oh, defenders of the science. Oh, oh, we've got a sigma, so we'll use a z. If we're stuck with s, then we're going to use a t. Put in the equation to get a z-score. We're going to add the variance if we've got two more. Oh, oh. So far for this chapter, you probably feel like there's so many pieces, it's hard to know which equation to use, it's hard to know what scenario you're in. So let's do the map, which is a decision tree, and that'll help you to figure it out. The very first question you should ask yourself is, what am I testing? There's two options. It'll either be a numerical thing, which you're testing the mean, or something categorical where you're testing proportions. We have not explored this side of the map yet. We will get there. We've been trying to finish out this side of the map, which is means. If you know that it's a mean, which so far is the only thing we've done, the next question you would ask yourself is, how many means am I testing? Either one or two. We've explored both of those. There's also a mean going in a linear pattern, which leads to regression, and we'll do that a lot later. But for right now, one mean and two mean. In either case, there is this wall that you have to get through called, is it normal? If it's not normal, that's when you're stuck, and that's when you say cannot do. There are two ways that you can get past this wall. Either it says it's normal, in which case you get a free pass, or you have more than 30 data points, and that's when we're going to use the central limit theorem and say it's okay to keep going. If you had two means, it could still say it's normal, or you would need more than 30 data points in both of those groups, and then that would allow you to use the central limit theorem and get past this wall. For one mean, once you're past the wall, the next question you'll ask yourself is, do I know sigma? If you do know sigma, that takes you to the very first type of hypothesis test we did, which was a z-score. If you don't know sigma, but it's s, that will take you instead to a t-score. But the equations are similar. Both of them take x bar minus mu on top, and both of them take the standard deviation divided by the square root of n. For this case, our standard deviation is a perfect standard deviation without error, whereas this one is a standard deviation coming out of data that does have error. I'll tell you which of the two is more realistic. We started with this because it's simpler, but real life is going to use this a lot. Now, I hope you see the similarity here. If you get that, it's not going to feel like we're learning anything different. It's going to feel like there's only one tiny change. This n-1 right here is to remind you of degrees of freedom. Please do not make the mistake of trying to multiply your t-score by n-1. This doesn't actually show up on the calculator. It only shows up when you go to the applet and put in your degrees of freedom. Now, the equation for the confidence interval is the same as this one, except we've rewritten it. If you don't get how these two equations are the same, please talk to me. It really should be equals mu, except your math teacher would say equals is wrong because this is a range and this is a value, so they would want a belongs to. And so sometimes we just leave this part out. But the confidence interval and this equation are the same. There's one equation, not four equations here. Let's go back up to the two sample scenario. If you have two samples and you know it's okay to be normal, the next question you'll ask yourself, is it matched pairs? And being able to tell whether it's matched pairs or not is important. Now we've skipped the question, do you know sigma? Because sigma is not very realistic to know. This is the only scenario we play with it. The rest of the time we're going to assume you don't know sigma, and that's why all these are t-scores. The difference between matched pairs and not is the first two data points in each group are linked specifically only to each other for some reason. They're twins from the same parents. They were born in the same year. They have the same income level. There's something about them that links those two to each other. Then it's matched pairs. The equation for matched pairs is really the same equation as the one sample t-test, except mu is specifically 0 for this case, and that should just make sense if you understand the idea of testing two groups against each other. 0 means they're equal. And we put little annoying D's on everything to remind you, you're not looking at group 1 or group 2, you're looking at the differences as you do them across each value. And so it's x bar d, sd, and nd, and here it's just degrees of freedom. That's not actually something you put in the calculator. It's only to remind you that you need that degrees of freedom in the applet. If it's not matched pairs, that's the independent test, which looks like the equation is twice as big, but it's really Okay, actually the equation kind of is twice as big, but it's not twice as big with two different things. It's just the same thing twice. 2x bars, 2s over the square root of n's. We did have to square them into variances, and we spend a lot of time talking about that. If that doesn't make sense, come talk to me. And for the confidence interval, same idea, 2x bars, 2 standard errors, but still 1 t-score. We're going to use the small n minus 1 as our degrees of freedom because of all the different rules we could use. That one's the simplest. So this should look exactly like everything we've done from the very beginning. There's only one equation on the board with slight changes according to which of these scenarios. And if you follow this map, you should be able to figure out what equation you need and which scenario you're in. Now, I want you to look carefully right here because as soon as you're done with this video, you're going to forget everything you learned all chapter long.